Hello, this is Richard Collins, your instructor in ATM 101, Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Today I want to talk about the solution to Problem 2 in the practice final exam. Problem 2 explores issues of atmospheric moisture, humidity, and precipitation. Starting with the multiple choice questions. A. As a parcel of air rises in the atmosphere, which of the following occurs? Before we start, let's think about what happens in a parcel of air as it rises. A parcel of air rising in the atmosphere must expand because it's moving into lower pressure. If it's expanding, it's pushing back the air around it, so it's doing work against the pressure around it, and therefore it must cool because the source of energy for doing that work is the internal energy of the parcel, which is its temperature. Therefore, rising air is cooling air. Therefore, the saturation vapor pressure of the water decreases because you know the capacity of air to hold water decreases as the temperature cools. As the temperature cools, atoms and molecules move slower, and water molecules moving slower, when they hit each other, they stick together electrically. If you go back to the structure of water molecules, and therefore sticky water molecules have a better chance of sticking together and condensing when they're moving slower at lower temperature. So air has less capacity to hold water as the temperature decreases. Therefore, the saturation vapor pressure, the pressure exerted by water molecules in the air when it's saturated, has to go down. The temperature decreases. That also happens. The relative humidity increases because relative humidity is the ratio of the amount of water present to the maximum amount of water vapor present, the saturation vapor pressure. If the saturation vapor pressure is going down and the amount of water stays constant, then the relative humidity must increase. So the answer is 4, all of the above. B. As the temperature of a mass of humid air decreases, which of the following occurs? As the temperature decreases, the relative humidity must increase, following the logic in A. Which is the best indicator of the actual amount of water in the air? C. The answer is dew point temperature. Dew point temperature is the temperature at which condensation should occur. It is the temperature that you cool a parcel to reach 100% relative humidity. It is the temperature that you have cooled the parcel such that the actual vapor pressure of water in the parcel has now become equal to the saturation vapor pressure, and condensation occurs. Relative humidity 1 is a relative measure of humidity based on the saturation vapor pressure at that temperature. It's a likelihood of condensation to occur. So 100% relative humidity says condensation will occur. 5% relative humidity says it's unlikely for condensation to occur. But it doesn't actually tell you how much water is present. In a warm parcel, you can have a very low relative humidity with lots of water present because the air can hold lots of water. The air temperature doesn't tell us about the actual amount of water in the air, and the saturation vapor pressure tells us the maximum capacity of the air to hold water, but it doesn't tell us how much of that capacity is being used. So the answer is 2, dew point temperature. D, which of the following is the least humid air? And the answer here is to look for the lowest dew point temperature. And so the relative humidity numbers are essentially a red herring. That's the point of the problem, that you're distinguishing between relative humidity, dew point temperature, and absolute humidity. Absolute humidity is associated with dew point temperature. And so we go to the lowest dew point temperature, which is the 15 degrees Fahrenheit, which is a relative humidity of 100% in this case. E, as a humid parcel of air falls in the atmosphere, which of the following occurs? If a parcel is falling in the air, it is increasing in temperature, the relative humidity decreases, and the mixing ratio of water remains constant. That's the other thing, that the total humidity in the parcel, unless there's rain occurring or condensation and cloud formation, the amount of water vapor in the parcel isn't changing as it rises and falls. So the mixing ratio, the ratio of the amount of water to the total amount of dry air in the parcel, isn't changing, but the likelihood of condensation and cloud formation is changing. And again, that's why as atmospheric scientists and meteorologists we're interested in relative humidity as we track cloud processes. So now we move on to problem F, and I'm going to turn the page to look at the figure as I discuss the answers to the problem. So in this diagram we have three curves. We have temperature plotted as a function of altitude for three curves, and the three curves, giving the answer ahead of time before I discuss it, the first curve is BCF, which is the curve that is red with red lines and red squares, and this is a temperature profile just measured on a given day if we launched a radiosonde. The curve BDE, the dashed red curve with the white squares, is the curve of the temperature of a parcel if a parcel was to rise in the air. If you could nudge a parcel upward from the ground and it floated up into the air, this would be its temperature curve. And finally, the curve AD is the dew point temperature curve for this parcel as it travels up in the air. And it's short-lived, and we'll talk about that. It only goes from A to D, and why is that? The thing to remember here is, how do I recognize these curves without memorizing them? The first thing is, for a parcel to rise in the atmosphere, it has to be less dense than the air around it. If a parcel is at a certain pressure and the atmosphere around it is at a certain pressure, the only way it can be less dense than the air around it, following the ideal gas law, is if it is warmer than the air around it. So a parcel can only rise in the atmosphere as long as it stays warmer than the air around it. We know that a dry air parcel, when it is nudged upwards, will cool at a rate of 10 degrees Celsius for every kilometer. So if it's cooling as it rises, but it remains warmer than the air around it, it will continue to rise. And so that's what we have here in going from B to D. The temperature of the parcel on the ground is the same as the air around it, but it starts rising. It may be nudged, it may be a wind effect, it may be that it's slightly moist or something and it gets nudged upwards, but it begins to rise. And so from A to D in the first 500 meters, it's cooling, but it's still warmer than the air around it. But we notice at D, the dew point temperature is now equal to the parcel temperature. So what has happened between B and D is that as the parcel has risen, it has got colder, its saturation vapor pressure has decreased, its relative humidity is rising as it rises. At the ground, the relative humidity was less than 100%, but at D we get 100% relative humidity because the dew point temperature and the actual temperature are the same, and we get the bottom of the cloud forming. And that's what we get in cumulus clouds in the afternoon, a very abrupt, sharp lower edge to the cloud. The cloud now continues to rise, but now we have latent heat release, and the cloud is rising, changing temperature now by only 6 degrees per kilometer. So you notice that there's a kink in the curve, and we're now cooling less quickly with height than we were. And we continue all the way up to E, at which point we find that, oh, we're now as cold as the air around us. And so we stop rising. And so the cloud exists between D and E, which is the period where the rising air is condensation is occurring, and we actually get to see the small water particles that are a cloud, and on a summer afternoon this would be a bright puffy cumulus cloud. So if I go down through the answers given that scenario, which curve represents the ambient air temperature? It's BCF. Which curve represents the temperature of the air parcel is BDE. And the curve that represents the dew point is AD. And dew point temperature falls 2 degrees Celsius per kilometer. So in this curve, the dew point temperature drops from 29 to 28 Celsius in going 500 meters or half a kilometer. The actual temperature of the parcel goes from 33 to 28, a fall of 5 degrees Celsius in half a kilometer, 10 degrees Celsius in a full kilometer. The relative humidity at the ground is less than 100% as the dew point is less than the air temperature. The relative humidity reaches 100% at 500 meters, point D. The altitude of the cloud base, condensation begins, is 500 meters, point D. The cloud rises to 2,000 meters, which is point E. The parcel temperature decreases 10 degrees Celsius per kilometer below the cloud, and it decreases at 6 degrees Celsius per kilometer in the cloud because of the latent heat release from the condensing water. If we increase the dew point temperature to 31 degrees Celsius, I would move my blue line at A over to 31 degrees Celsius, and I would draw a line upward like the blue, parallel to the blue line, and that would intersect the dashed red line at 250 meters, the first horizontal line in the plot. And so now the cloud, if it was more humid, would actually form at lower altitudes, at an altitude of 250 meters. And this is what happens in the United States. As you go from east to west, the continent generally gets drier and cloud heights get larger in the west than they are in the east. When it's more humid in the east, clouds form at lower altitudes. Finally, based on this plot, in general, does the height of clouds increase or decrease as the humidity increases? And again, the answer is decreases, and that's actually what we see in cloud populations around the world. Now we look at part G of problem 2, and it's a long sentence. I want to highlight where the question marks are. What is the saturation vapor pressure? What is the relative humidity? What is the dew point temperature? There's then a statement about Delta Junction and Bethel, and then we get to the next question, which is which location is less humid? Is the relative humidity higher or lower at the less humid location? Briefly explain why. And there's actually a typo in this solution that I'll point out as we go through it, and I'll post it on the announcement page. First, the saturation vapor pressure is the partial pressure of water vapor in air when the air holds as much water as the temperature will allow. So it's the amount of water represented as a pressure, because you know if you have a mass of gas, it will exert a pressure. It's the partial pressure because it's just the pressure exerted by the water molecules. It's not the pressure of the whole air parcel. And water can only hold as much air can only hold as much water as the temperature will allow, and as the temperature increases, the capacity of air to hold water increases. We are saturated when we're holding as much water as we can. The relative humidity is the ratio of the amount of water present to the maximum amount of water vapor that the air can hold. So it is the partial pressure of the water vapor divided by the saturation vapor pressure. The relative humidity goes from 0% to 100%. 0% is no water present, no partial pressure of water. 100% is that the partial pressure is equal to the saturation vapor pressure and condensation is about to occur. The dew point temperature is the temperature a humid air parcel must be cooled to so that it is saturated. And the goal here is that if a parcel is not saturated, then the partial pressure is less than the saturation vapor pressure at that temperature. As we decrease temperature, the saturation vapor pressure decreases until the saturation vapor pressure is equal to the amount of water pressure present. And at that point we get condensation, and if you will, by cooling the parcel we squeeze the water out of the air as dew. Behind these definitions is the concept that cold air can hold less water vapor than warm air, as we've discussed earlier. Concerning Delta Junction and Bethel, Delta Junction in this case has to be less humid than Bethel because it has a lower dew point temperature, even though it has a higher relative humidity. Delta Junction is less humid than Bethel because it has a lower dew point temperature. The relative humidity in Bethel is actually lower even though it's more humid, and this is where there's a typo. I said the relative humidity in Bethel is higher, it's actually lower. And the reason for this is that the saturation vapor pressure is higher in Bethel than it is in Delta Junction because the air is warmer and can hold more water vapor in the air. So while Bethel is more humid, it's less likely for condensation to occur at Bethel than Delta Junction. The final question is H, where we look at a plot of relative humidity, dew point temperature, and temperature as measured on the 15th of April that you've looked at in Unit 15 of the class, where you've looked at weather over the week of April in interior Alaska. So the first point is just looking at the plot, where do you think condensation might occur? And condensation is most likely to occur when the relative humidity is highest, which is at 6 o'clock in the morning. We have about 80% relative humidity, whereas at 6 o'clock in the evening, 1800, the relative humidity is lowest. briefly explain how the relative humidity varies through the day in terms of temperature, saturation, vapor pressure, and dew point temperature. And the reason I'm looking at this plot is that we have a beautiful diurnal cycle for April. It's a textbook case of the atmosphere is warmest in the late afternoon. As the sun goes down in the late afternoon, it begins to cool. It cools through the night into the early morning, and then in the early morning it begins to warm again. It's a classic diurnal cycle, a daily cycle of temperature. The reason for this data being of interest to us is that the dew point temperature is relatively constant. It only varies by a couple of degrees, which tells us the amount of water vapor in the air is really more or less as constant as you could get on this day. And therefore, if the dew point temperature is staying constant, that means the amount of water in the air is relatively constant over this 24-hour period. So the relative humidity is fluctuating not because the amount of water is changing, but because the capacity of the air to hold water is changing as the temperature changes. When the air is coldest at 6 in the morning, the saturation vapor pressure is the lowest, and therefore the ratio of the actual vapor pressure to the saturation vapor pressure is highest, and the relative humidity is highest. In the warmest part of the day, the capacity to hold water vapor is highest, the saturation vapor pressure is highest, and therefore the relative humidity is lowest. So here we see the relative humidity changing dramatically through the day, but the actual humidity isn't changing dramatically through the day, and that's what we want to highlight here. The last, which of these statements would you agree with? The answer is B. There's a stable air mass over the state, and the reason for this is because the water vapor isn't changing through the day. So the humidity, which would be carried in different air masses, isn't changing. If a marine air mass was replaced by a continental air mass over the state, we would expect the dew point temperature to drop through the day as air that was absolutely humid, a marine air mass, was replaced by an air mass that was absolutely dry. And that's not what we're seeing. We're seeing the relative humidity vary through the day, but we're not seeing the dew point temperature vary through the day. So the answer is B. Finally, I just want to point out in this case that the curves are labeled in the diagram. The dew point is the blue with the white triangles. The temperature is the green curve with the green squares, and the relative humidity is the dashed red line. I noticed that the caption in the bottom of the figure got run off, but all the information is there.